Hello, my name is Rob Reynolds. Welcome to Calculus section 7.2. Today we're going to learn about integration by parts. And here's the general formula. Basically, it's used for when you see a product. We know that if you have the integral of a plus b, that's equal to the integral of a plus the integral of b. But we also know that the integral of ab does not equal the integral of a times the integral of b. So we're going to learn what it does equal today. So integration by parts, we're going to find an indefinite and a definite integral, and we're also going to look at some word problems for future income. So integration by parts works really well when you have a product, x squared and e to the x, and your u sub doesn't work. So we've been studying techniques for integration, and this is another technique that we're going to learn. So both of these are great examples where you may want to try to do integration by parts. Here's just a quick little proof of why the rule works. It's derived from the product rule, which kind of makes sense because if you can do it forward, then you can do it backwards. So if you're interested in pausing the video here and looking at this, but this is how you derive, this is where the formula comes from, the product rule, which you already know, 1d2 plus 2d1. So the general rule of thumb is you're going to let dv be the most complicated, but sometimes that's frustrating to me as well. I always go, well, this is what your book offers, but I always let dv be something that I can integrate. So just make sure that you're choosing dv to be something that you can take the integral of. If you don't know what the integral of it is, then that's probably not good to let dv be. So what we're going to do is choose a u, and from the u we can find du, and then we're also going to choose a dv, and then from the dv we could integrate dv to find the v. So we could always just make a quick little chart here, which sometimes is helpful. So you need to find these four things, and this top row is going to come from this over here, and that's why the book is saying let dv be the more complicated. Well, if we follow that rule, the more complicated is e to the x, and certainly we can integrate e to the x, because if that's the derivative of v, all we have to do is take the integral of the derivative of v to get back to v. So the integral of e to the x is just e to the x. And that leaves x as the u sub, and then the derivative of x is 1, and we'll say, well, yeah, that's 1 dx. So I'm going to use my rule, which is the integral of u dv, and we've let all of this be my dv, e to the x dx, and then we are going to say that's equal to uv minus integral v du, and I'm simply just going to plug in everything from my chart that I found. So uv minus integral v, well, the integral of v is the integral of e to the x, which again is e to the x, plus c, and then I can factor out an e to the x, leaving me with just x minus 1 plus c. So there's your first look. Let's take a look at another example. Here's how the author decide to work it out. So again, we have all sorts of choices on this, on what to let dv be. I think this choice is the best. So again, here's the author's explanation of that same problem, and lo and behold, they get the same answer. Well, they didn't factor out an e to the x, and then they go and check it, and they say, oh, to check that, all we have to do is take the derivative of that and see if we get back to the original problem. So here we go. Here comes another example. Now I know what you're thinking. The derivative of a natural log is 1 over x, but the integral of the natural log is not 1 over x. So let's not go down that road. That's just wrong. So again, we need to choose a u and a dv, and let's go ahead and make our chart again. U dv, after that we'll have a du and a v. So if I choose the more complicated in this case, well, I don't know. Looks like the most complicated thing is the ln of x, but if I choose the ln of x here, I don't know the integral of the ln of x, and that's what I'm saying. That rule that choose the most complicated doesn't always work for me, although that's what the author says. I always say just make sure it's something that you can integrate. So I know I can integrate dx, so I'm going to choose the dx to be my dv, because if I integrate dx, I'm just left with x. And then that forces this to be the ln, and I do know the derivative, at least the ln of x, is 1 over x. So now I'm going to go back to uv minus integral v du, which is the rule that I'm going to have memorized. Let's see, under here, I'm sure, yep, they choose the same thing. I don't know if I can get my pen to work. There you go. So this is just showing you a little discussion of what we should let u and v be. So once we do that, then I'll plug in again uv minus integral of v du. Well, not exactly. Let's see. This is the integral of x is my v, and then du is 1 over x. And of course, I dropped it, but I have a dx there. Dx. And then that says x ln x minus just the integral of dx. And the integral of dx is just x. So x ln x minus x. Of course, I could factor out an x, but it didn't look like the author did last time, so maybe I'll just leave it. Let's see if the author factored it this time. No, they just left it. So from this day forward, we're going to say just memorize no. I'm going to give you a cheat sheet on this, and this happens quite a bit, this integral of ln x. And so when I teach to my face-to-face class, I say, hey, this is an important thing. Just like we know the derivative of sine is cosine. That's just some things we just have to memorize. We don't want to look them up in a cheat sheet because they're kind of important. We need to recognize them. So I encourage my face-to-face class to kind of recognize this. But since you're my online class, or if you are in my online class, I'm going to give you a cheat sheet, a little bit of buy on the memorization. So I'm backing up to example number 2. I went out of order because I thought example 3 was a little bit easier. So I'll make my chart again. U, dv, and v. And I'm going to do the same thing. This I don't want to let be the ln because I don't know the integral of that. Well, I do because I just found it out from example number 3. But let's suppose that I didn't do example 3 before. So again, I would still say x squared dx. So x squared dx is my dv. And if I integrate x squared dx, then I get 1/3 x cubed, because remember, when you integrate, you increase the exponent, and when you take the derivative, you decrease. So I'm going to be taking the derivative over here, but I don't have to decrease because that's just the derivative of the ln of x, which we know is 1 over x. So once again, uv minus integral v du, and I'll get the x cubed over 3 ln x minus, this is x cubed over 3 times my dx, that looks like du. Okay, wait a minute, I lost myself. That is a u. Enter uv minus integral v du, and the du is 1 over x, and I've got a dx here, which I dropped from here. So when you took the derivative of u, then of the ln of x, then that's 1 over x, and then times the dx. That's where the dx is coming from. So this simplifies here to be x cubed over 3 ln of x minus the integral of, well, I can pull out the 1/3 x squared dx. So this is x cubed over 3, the ln of x minus 1/3. Now, I'm integrating again, so I'm going to increase, and that's be x cubed over 3. and then minus x cubed over 9. And again, there's some things that I could factor out, plus c, but let's see if the author just kind of leaves it like that. Yep. So I don't know why he's not factoring. Usually in calculus, we like things in factored form. Example 4. Example can be worked out the traditional way, but I'm going to introduce a shortcut method as well. So if we let u be x squared and du be 2x dx, and then dv be e to the x dx, and I integrate that, I'll get e to the x, then I can do my uv minus integral v du technique, but I'm going to have to do another, so you can see I've got, I got another product here, and I've got another integral of u v du, or u dv. And so you can see I've got to split this up again into another chart. But I think if I pop out the 2, I've done something very similar to this already. X e to the x dx. If you look back, I think this is example number 1 that I've kind of solved for that. So I'm going to leave this blue out here. X squared e to the x minus 2. And then if you look back at example number 1, it was x e to the x. Well, I'll distribute the 2. And then I can factor out an e, which again, I don't know if the author is doing that factor or not, but in this time I am. All right, that actually is a harder method. Well, I actually had to do I had to repeat. I had to do the integration by parts repeatedly, twice. There's a shortcut method that your book does not introduce that I would like to introduce to you. I think you're going to kind of like it. If we make a column for your derivative and then make a column for your integral, and remember we were taking the derivative of your x squared term, and then we were integrating e to the x dx. Watch what happens if you just keep taking the derivative of this. So the derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 2 is 0. And it's important that you be able to get to a 0, otherwise you can't do this technique. And then for the integral, if the integral of the function just keeps repeating itself, that's when you want to use this technique. So you won't always be able to do this. But in this particular case, since the integral of e to the x is e to the x, it works nice. It also works for like sines and cosines. If it wraps back around, it might take a while for it to repeat, come back around, but eventually it will. So look what happens if I take these diagonals and multiply them together. So I got a green diagonal, a blue diagonal, and then a pink diagonal. And I'm going to start with positive, and then I'll switch to negative, and then I'll go back to positive. And then I won't worry about the 0, because 0 times anything is just 0. But look what happens if I don't put it in factored form. Here's the green product that I had right here. Here is the blue product that I had right here. Notice that negative gets picked up. And then, of course, here's the pink product. Isn't that nice? Plus C. So that worked really slick, and you're welcome to use that technique again if you can. The book doesn't explain that technique, but boy, that sure is. It's better. Look, here's the authors. Oh my gosh, it's just, they just keep. Oh, fine. They did finally factor this thing, but notice that it's easy to get this form from that cheat technique. So if you ain't got time to do all that long problem, then you can go back and do this method. Of course, you can YouTube these methods as well. I grabbed this as a snapshot right off of YouTube. This is a slightly different problem. They used an x cubed. We just got done with an x squared, but it's the same concept. And here's the answers in those diagonals. Also, you can look up Wolfram alpha and see that first diagonal was e to the x cubed. That was positive. Then the next one's going to be minus 3x. So I just went ahead and showed you the Wolfram alpha answer for this. And then, of course, we had a 6x and a negative 6 that followed right there. There's the 6x and the negative 6 that followed. So I encouraged my class when I went through this to kind of do this the easy method, meaning choose a derivative, choose the integral, and see if you can't just find those diagonals to go through. Remember, you've got to hit a 0 on this side, otherwise that technique won't work, and these have to be repeaters. Well, at least eventually a repeater. So I'll leave this up to you, and again, you can always just Wolfram Alpha this to come up with the correct answer. There's the answer. See if you can't pause the video and get that on your own. If you can't, shoot me an email. A couple other things about integration by parts. There's a lot of techniques. We just are introducing another techniques, and you need to recognize the formulas. And this is why I'm not a big fan of formula sheets, because you really kind of need to just recognize these formulas in the form that they're in, so you'll know which technique to use. Because we don't always want to be using integration by parts, especially if you can use a U sub, which is much easier. So I like this slide because it looks like, well, we just looked at this one. Yes, the integration by part works well here, but this one might look like an integration by parts, but remember, you could do a quick U sub for this. And here, sometimes we have log rules that we can apply that would really help for coming up with the antiderivative. So as you gain experience through these integration techniques, your skill in determining whether I should be using a U sub or a log rule or a power rule will increase. But again, for this particular lesson, we're looking for problems with integration by parts. And so we'll continue with example number 5. So example number 5 looks exactly like example number 3. If we just skip to the answer for number 3, we had an indefinite integral, and now we have a definite integral, and it says just go ahead and evaluate that from 1 to e by doing the fundamental theorem of calculus. So evaluate the function at e, and then evaluate the function at 1. So a little bit of log rules here. E to the ln of e minus e, that's all the f at e, and then the f of 1 would be 1 ln 1. Do you know what the ln of 1 is? That's a 0 minus 1. So 0 minus 1 here, and then the ln of e is 1, so that's e minus e, which hopefully you know as 0, and 0 minus negative 1 becomes a positive 1. So good, the author gets the same thing. So all we're doing is then applying the fundamental theorem of calculus to this as well. One last example that I haven't shown you is using the sign. So again, I kind of mentioned that you could use the the derivative and the integral technique for that, and you can practice that. But for the sake of integration, it says show integration by parts, so I would want to show that you could do this. So if it specifically says use integration by parts, we should probably use that. So I think the more complicated here is the sign. So I'm going to follow the book's suggestion and let the more complicated be sign. And then the integral of sine is negative cosine. And the derivative of x is, of course, 1 and dx. So here's my uv minus the integral of v du. And that's going to be negative x cosine x plus, and the integral of cosine would be sine, because there's two negatives forced to positive. And so I don't know which way is faster. This certainly wasn't bad. But again, if you wanted to try this method, you could. But since it says use integration by parts, I would recommend doing that. So here's that author. Again, here's another example of a repeated. I'll let you run this scenario because the video is getting a little bit long. But this is a difficult problem, and I don't think I'll test over anything of this magnitude. Sine x dx, and then v is equal to negative cosine x. So when you get done, you're going to end up with the integral of e to the 2x cosine dx, and you're going to have to repeat the u v minus integral v du from that. So this is just a scary problem. I think a 2 is going to be hanging out there. So I'll let you try to work on this, but there's a little trick in this problem that you'll catch more in Calc 2. My goal is to try to introduce these things to you, but you'll see these can get really complicated pretty fast. So I'm going to end the video here. Remember, if you're in terms of theta, then the derivative of theta would be d theta, and if dv is secant squared, this is kind of where I hope you know a little bit about the integral of secant squared is tangent theta, and so this is the u v minus the integral of v du. And then I don't know if you know the integral of tangent, but again, I'm going to be providing a cheat sheet for you, so you could look that up. But maybe you have that memorized. That's the natural log of the cosine of theta. So I just wanted to show you some things keep popping up that we keep seeing over and over again, and eventually you might want to kind of get those memorized so you can recognize those. So don't be 100% dependent upon cheat sheets. It's kind of nice when you've worked enough problems, you can kind of recognize, oh, I remember the integral of tangent. It doesn't pop, you haven't seen it a whole lot yet, but you're going to see that more and more and more through your calculus, especially if you're heading on to Calculus 2 and Calculus 3. So there's a couple other examples. I'll leave those for you. The worked out solutions are here. Actually, these are just problems from your book, and you're welcome to open up your book and work any odds and check the answer in the back of the book. Remember, you've got Wolfram Alpha, a nice little website that you can check all these answers. And then Symbolab will actually give you step-by-step solutions. So try, if you haven't been to Symbolab, Google Symbolab, and then type in one of these things, and they'll show you step-by-step how to work it out. If you have any questions, feel free to email me. Thanks.